Okay, let's go ahead and continue on with our notes. So we're gonna introduce a couple theorems and postulates. Maybe you've heard those math words before, maybe you haven't. As a quick little definition, theorems are things that are proven. Some mathematician out there took the time to prove them to make sure that these things are always true. Postulates, however, are things that are not proven. These are just things that are accepted by everyone to be true. They are the basis of mathematics, and it is on postulates that we are able to build theorems. So our first theorem here is the vertical angle theorem. This is if two angles are vertical angles, then they are congruent. So that was a definition that we were using that on our homework problems, but it is a theorem that somebody proved that two angles that are vertical angles are congruent. Okay, the next one is a postulate. This is the corresponding angle postulate. So this says if two parallel, and the symbol that we use for parallel is two sideways lines. If two parallel lines are cut by a transversal, then each pair of corresponding angles is congruent. So again, we were using this on your homework that corresponding angles are congruent, but that is just a postulate that is accepted. Okay, and the next definition, well, not definition, the next theorem we're going to talk about is the alternate interior angle. As you've seen, these are not things that are new to you, but they're just theorems themselves. So we need to show that they're theorems. So the alternate interior angle, this is if two parallel lines are cut by a transversal, then each pair of alternate interior angles is congruent. So this one just says the alternate interior angles are congruent. And our final one is the perpendicular bisector theorem. And this states that any point on the perpendicular bisector of a segment is equidistant from the endpoints of the segment. Okay, so what we mean by that is if we have a perpendicular bisector, something like that, perpendicular bisector, and it is perpendicularly bisects between these 2 points. Any point on the perpendicular bisector, if you draw a line from that point to these original endpoints, these 2 lines must be congruent. So if we were to draw them like here and here, those would be congruent, or from here to here, those would be congruent. So any point on the perpendicular bisector, if you draw lines from that point to the endpoints down here, then those 2 lines have to be equal. That is what we mean by this theorem. So we are going to go ahead and prove some of these theorems since they can be proven. You will have a couple proofs on your homework. I'm going to help you with them. Proofs, when you first learn them, are really complicated and really hard. And it honestly wasn't until college that I really understood what a proof was, and I really found them enjoyable. So if you feel like these are really hard, it's okay. I'm going to help you through them, but do your best to follow along with me and digest what we're talking about. So we're first going to prove the vertical angle theorem. So let's say that we were given the angle AEB and angle DEC are vertical angles. Okay, that is all that we know, is that angle AEB, so angle AEB, and I'll maybe do this other one in a different color, and angle DEC, all we know is that they're vertical angles. They're across from each other. And we want to prove that angle AEB is congruent to angle DEC. Okay, so we don't know that they're congruent yet. We're going to prove it. So how proofs work is you always start by writing down what you were given. So the reason for this first step will always be, this is what you were given. So we were given the angle AEB and angle DEC are vertical angles. Okay, and then we try to figure out like what we can do with that information. And if we look up at our picture here, we can see that angle AEB is supplementary to angle BEC. Right? Because BE from C to A, that's 180 degrees. Okay, we feel good about that. And then angle DEC is supplementary to angle BEC. Alright, so DEC and BEC are there, and then AEB and DEC would be here. So yeah, those make supplementary angles. So we can conclude that one because angle AEB and angle BEC, as well as angles DEC and angle BEC, these two, they form straight lines. Right, that's what we just looked at. These form straight lines. Okay, so because they are supplementary, well, we know that they must add up to 180 degrees. So we know that the measure of angle A plus the measure of angle BEC. We use that little m when we're talking about if we're trying to quantify the angle, it's the measure of it. It's going to be equal to 180 degrees, as well as the measure of angle DEC plus the measure of angle BEC is 180 degrees. And we conclude that because of the definition of supplementary angles. Okay, so if we rearrange those equations, then let's scroll down a little bit. We can say that the measure of angle AEB is equal to 180 degrees, subtract the measure of angle BEC, right? If I just subtract measure of angle BEC from both sides. We can also then say that the measure of angle DEC is equal to 180, subtract the measure of angle BEC. Okay? And we can conclude that by what's called the subtraction property of equality, which is a fancy way to say that we can use subtraction in these geometry equations. So this statement here and this statement here are the same. So that must mean that the measure of angle AEB equals the measure of angle DEC if they're equal to the exact same thing. And this is called the transitive property. So that's what we do when we take two things and set them equal to each other. And because the measures are equal to each other, that then means that the angle AEB is congruent to the angle DEC, which if you look up here, that's what we were trying to prove. So that's awesome. We know that we're done. And the reason that we can conclude this is because angles with equal measure are congruent. Okay, so essentially what that proof is it's just meant to be a way to lay out how you can logically go step by step to say, hey, if we know this, well, then we know this, and we know this, and we know this, which means we can conclude something such as two angles are congruent to each other. Okay, let's look at another one. So now we are going to do the proof of corresponding angles. So let's say that we were given that line Q is parallel to line R. And we also know that angle 1 and angle 5 are corresponding angles. So they're just located at the same position on our image. And we want to prove that angle 1 is congruent to angle 5. So again, we always start with what we were given. So we were given that Q is parallel to R, and the angle 1 and angle 5 are corresponding angles. Okay, then what can we do with that? Okay, well, I guess we know that angle 1 and angle 4 are supplementary, right? Because those are on the same line. Which if they're supplementary, that means that the measure of angle 1 plus the measure of angle 4 is equal to 180. And we can do this by what's called the straight angle theorem, meaning they're on that same line. Okay, we also know that 4 and 5 are supplementary. If we're looking at 4 and 5 here, those are same side interior angles. These are same side interior angles. So we can conclude that they are supplementary. And because they're supplementary, the measure of angle 4 plus the measure of angle 5 must be 180 degrees. Well, we're going to do the same thing that we did above and rearrange those equations. So if we subtract, we can get, for one of these, we can get the measure of angle 1 is equal to 180. Subtract the measure of angle 4. For the other, we can get the measure of angle 5 is equal to 180. Subtract the measure of angle 4. And again, that is the subtraction property of equality. And again, these sides are the same, so we can conclude that the measure of angle 1 must equal the measure of angle 5 by the transitive property. And because their measures are the same, we know that angle 1 is congruent to angle 5. So angles with equal measures are congruent. And that is in fact what we were trying to prove. So we know that we are done. All right, right below this, we have a paragraph proof. In the math community, this is most often how proofs are created. They're not written out as tables, they're written out as paragraphs. This paragraph does say the exact same things as the table above. And we just added this in here so that you could see an example of a paragraph proof, even though in this class, table proofs are going to be just fine. Okay, let's do another one that's a little bit shorter. So example number 3 here, this is the proof of alternate interior angles. Let's say we were given that Q is parallel to R. That is all we know. And we need to prove that angle 3 is congruent to angle 5. So we're talking about angle 3 and 5 here. Okay. Well, because we did we start with what we're given. We're given that Q is parallel to R. And since we proved the vertical angle theorem earlier, let's try to use that. So, well, angle 3 is vertical to angle 1. And because we proved that vertical angles are congruent, we can actually just start there. So we know that angle 3 is congruent to angle 1. And angle 5 is also congruent to angle 7. So this is that vertical angles are congruent. Okay. And then we also know, because we just proved, I guess we didn't prove this. Did we? That was the same side. Yeah, we didn't prove this, but we're going to use it anyway. We know that angle 1 is congruent to angle 7 because angle 1 and angle 7 here are alternate exterior angles. So alternate exterior angles are congruent. Okay. And then if we look at those, we can see then that angle 3 is congruent to angle 1, and angle 5 is congruent to angle 7. So that means that angle 3 is congruent to angle 5 by that transitive property. And check that out. That is what we were trying to prove. So we're done. Okay, there's one more proof that we're going to do. However, in order to do this proof, we actually need to review some triangle congruency postulates. Hopefully you learned these in middle school, or maybe you did. But if you didn't, we're just going to go ahead and review them now anyway. So let's look at these. These are different ways to prove if two triangles are congruent. So the first one, it's called SSS, meaning side-side-side congruency. So if we had two triangles and we knew that those two sides were congruent, those are congruent, and these bottom ones are congruent, then we could conclude that the triangles themselves are congruent. We also have side angle side congruency. So if we knew this side and this side were congruent, this angle and this angle were congruent, and this side and this side were congruent, then we would know that the triangles are congruent. Something that's important about this is that these things have to be adjacent to each other. So I think about going around the triangle in a circle. Let's say I started here, I would pass a side that was congruent, and then I would pass an angle that was congruent, and then I would pass a side. And that's why it's called side angle side triangle congruency. They have to be in that order. The next one is angle side angle. So again, given two triangles, and if we knew that this side, this angle and this angle, this side and this side, and this angle and this angle were congruent, we could conclude that those triangles were congruent. And again, make sure that you just go in the proper order. I usually go counterclockwise, I guess. So this is angle side angle congruency. Okay, the next one, it is angle side. This would be if we had an angle, another angle, and a side going counterclockwise. I guess I could also go clockwise, it doesn't matter. Then we would be able to conclude that the triangles were congruent. And then the last one that verifies congruencies is what's called the hypotenuse leg congruency. This applies only to right triangles, so that's important. This is only for right triangles. If we were given two right triangles and we knew that the hypotenuses, which is the longest leg, the side opposite of the right angle, were congruent, as well as one of the legs. It doesn't matter which one, but one of the legs. If those things are congruent in the same positions on the triangle, then we know that the two triangles must also be congruent. I do want to point out that there are a couple of patterns that you can see in triangles that are not congruent. So things that are not congruent is if you have angle, angle, angle. If you know three angles of a triangle, that does not guarantee that they are congruent. In addition, angle, side, side, which if you see, that is a cuss word. So we don't cuss in math. That does not lead to congruency. So if that helps you remember, angle, side, side is also not a triangle congruency pattern. Okay, you're going to need those triangle congruencies in order to do your homework. You're also going to need them to do some of the proofs. So let's now look at example number 4. Okay, so let's say that we were given that line CD is a perpendicular bisector of line AB. And we need to prove that AC, line AC, is congruent to line BC. Okay, so we know CD is perpendicular, and we're trying to find that this line and this line are congruent, which is the theorem we defined earlier. So again, we start with what we're given. I'm not going to write it again. It's just that statement. Because it's a perpendicular bisector, we know that AE, line AE, is congruent to EB. Right, that's what it does, is it cuts that in half. So this is the definition of a perpendicular bisector. We also know, because it's a perpendicular bisector, that angle CEA is congruent to angle CEB. So those are just our 90-degree angles here. They are right angles by definition. Definition of a perpendicular bisector. Okay, we also know, this is kind of a funny thing to define, but we also know that line CE is congruent to line CE, which that makes sense because it's the same line. Well, let me show you why we care about all these things. We have one triangle here, and we have another triangle here. And if we can prove that those triangles are congruent, then we know that this angle, that line and that line must be congruent to each other. So right now, we have shown that AE and EB are congruent. We've shown that these two angles are congruent. And we've shown that these lines are congruent. And if you look at that, that would be side angle side congruency. So we can conclude that triangle CEA, be careful when you write these, they need to be in the same order, like you're talking about congruent angles. CEA is congruent to CEB, to triangle CEB. And we concluded that by the side angle side. Sorry, this one up here is what's called the reflective property. You can remember that, it's like looking in the mirror. It's the same thing. Something is equivalent to itself. And now, because we know those triangles are congruent, we can conclude that AC is congruent to BC. And this is what we're going to call CPCTC, which means corresponding parts of congruent triangles are congruent. I will write that on the other page here in just a second. Make sure you got that. If you need to pause the video, you're welcome to. I'm going to scroll back down to this. And the last thing that I want to add to our often used congruency statements is what we just used. And this means that corresponding parts of congruent triangles are congruent. Okay, let's look at a couple from your homework. So I'm going to scroll down to question number 21. So it says, state if the two triangles are congruent. If they are, state how you know. So looking at the two triangles on 21, we know we've got an angle here that's congruent to that angle there. This angle is congruent to this angle. But we also know by the reflexive property that this is equal to itself. And if we look at that, that's angle, side, angle. And fortunately for us, that is one of our types of congruencies. So we know that these are in fact congruent. So you'll just want to use, sorry if that makes anybody motion sick, this page and say, hey, angle, side, angle does in fact prove congruency. So I know down here that angle, side, angle does verify that these are congruent. Okay, so I'm going to let you guys do 22, 23, 24 on your own. Some of them are not congruent, some of them are. Okay, and then you have part B of your homework assignment. I'm going to help you with question 2 when I get back, just because as you can see, there's a lot of pieces of it. So don't worry about doing number 2. I do want you to do number 1. It's similar to what we were doing in the first part of the lesson. But I do want to help you with these proofs. I'm going to help you with number 3, and then I want you to give number 4 your best attempt. If you aren't able to figure it out, that's okay. We'll go over it next time, but I do genuinely want you to give it your best attempt, okay? So number 3 here, we're given that PA is equal to PB. So we know PA is equal to PB. We know that PM is perpendicular to AB. So we know all of those angles are right angles. And we need to prove that PM is the perpendicular bisector of AB. So again, we're always going to start with what we're given. So PA is equal to PB, and PM is perpendicular to AB, is what we were given. Okay, because they're perpendicular, as we drew on our image, we know that the measure of angle PMA is equal to the measure of angle PMB, which has to be equal to 90. That is the definition of perpendicular. Okay. Maybe we're going to try to use some triangle stuff here, because we've got a triangle here and a triangle here. Well, let's check this out. This is the reflective property. We know that PM is congruent to PM by the reflective property. Okay, well, if we look at our triangle here, we've got angle, side, side. Oh no, we've got angle, side, side. Congruency. We know that that does not fly in math class. Okay, so that's not going to be the answer here. Well, we are dealing with right triangles, so maybe we can use that hypotenuse leg. Well, this is the hypotenuse and this is a leg, so because we know that we have congruency patterns for those, that means these two triangles must be congruent. So triangle AMP is congruent to triangle BMP by HL congruency. And because those are congruent, we know then that PM is congruent to AB because corresponding parts of congruent triangles are congruent. And we have in fact proven what we needed to prove, so we're good to go. Again, go ahead and do number 4. Now that we have finished the video, you are now equipped to do all of the questions on your homework assignment. When I return, I will be happy to answer any questions that are lingering.